In this video, we are going to see another example of insertion in a binary heap. So we are talking specifically about a min heap. This is the exact pseudocode that was shown in the previous video. I've just modified it a bit to resemble the C++ code that you're going to write on Stepic this week regarding like heap insertion. So how this works is the first step of this algorithm is to insert the new element at the end of the array. So we already have this heap and we are trying to insert 11 into this heap. So what we are going to do is insert the new element at the end of the array. So this is the array representation of the heap. Now we are going to insert 11 at the last space that's available. Next, we are going to set the child to arr.size minus 1. So in this case, the array size was 14. I've taken just like some random size. Next, we are going to have a new variable that will store this child pointer that's going to point to size minus 1, which is 13, or it's going to point exactly to our child. So this is how the current state looks like. We have added 11. 11 has been added at this heap. Next, in the next statement, we are going to set the parent, which is now parent's value is being calculated, and that is equal to the same equation which we used earlier, which is child minus 1 divided by 2. So it will be 12 divided by 2, which is equal to 6. So parent is actually pointing to this node. And if you see the heap, it's exactly pointing to this particular value. Next, we are going to continuously run this loop, which is we are now going to compare the element to its parent and make sure it's satisfying the heap property. If it is not satisfying the heap property, we'll fix the property and move up and again check it. If it does satisfy the property, we are going to stop right there. So if it does not, if it violates the property, we are repeatedly going to check till it reaches the root node. So we are first checking whether this node 11 has a parent or not, or have we reached the root in this case. Next, we are going to compare the parent's value. Now 66 is greater than child. Like ARR of parent is what? Like 66. And ARR of child is 11. We are going to compare these two elements. Since 66 is greater and this is a min heap, 11 should be on the top. So we are going to swap these two values, which is these two will be swapped. 11 will go up and 66 will go down. Next, we are going to set the child equal to parent. So child will now be, instead of 13, 6, and parent will be equal to child minus 1 divided by 2 repeatedly, which is 6 minus 1 is 5, 5 divided by 2 is 2.5, and since we take the floor of this value, it's going to be 2. So in the next slide, we can see the child is was 16 and 6. We have first set this value in the previous case to 13 and 6. In the next one, after this comparison is successful, we are going to have new values of parent and child, which is the 6 and 2. Also, we have now swapped these two values. Now, one thing you have to note is, like, I think I'm going to describe you after the next swap, but I'll come to that. So now we are going to compare the values, which is this 11 is compared to 29, which is the child is now pointing to 6, which is this value, and parent is, as we said, like 6 minus 1 divided by 2, which is like 2.5 floor, which is 2. So 11 and 29 are being compared, which is these two elements in the heap. Now, since there's a violation, because 11 is smaller than 29, we are going to again do a swap and recalculate the value of child and parent, which is child will now be equal to 2 and parent will be 2 minus 1 divided by 2, which is 2 minus 1 is 1, 1 divided by 2 is 0.5, and the floor of it is 0. So you can see that this condition is now successful because it violates the heap property. So we are going to swap these two values, which is 11 and 29. We had a swap right here, also in our array. Next, we recalculate the values to 2 and 0 as I just stated. Now the child is pointing to the 2th index, which is this new index, which is 11, and the parent will now be pointing to the 0th index, which is 8. So we have, this is the child and this is the parent. In this case, this, like once we go back to this while loop, now it's going to check whether parent is greater than equal to 0. So since it is 0, like it still is fine. But the second statement, ARR of parent is greater than ARR of child, which is 11, is lesser than the parent. So in this case, the property is not violated. So that means we have reached our destination and we are going to exit the loop because it's not going to iterate that loop because of the violation of this, the loop conditional, or the property is in the correct place. Now, one thing you might be thinking of is, why does this work? Why doesn't we need to look at the left subtree or the other subtree to make sure this works? So the key idea is, like, since the properties of heap is parent should be greater than, less than both children in case of heap. So once we actually change or swap these values, if this value, like let's say if here it was like 29 and here it was 11, if we swap these values, since we are swapping 11 with 29, which is again like a lesser value to the current parent, we know that we are swapping with a lesser value, so it's automatically going to be lesser than the left subtree, and the left subtree's property is going to be is going to stay true. So that's why like this thing works, which is we just need to compare it to its parent but not to the left subtree or something like that. And basically, like whenever we are inserting an element in the heap, to add an element to the array, it just takes O of 1 because we just inserted the element at the end. Next, we call like Heapify up. So this entire algorithm, which is this while loop, this is called Heapify up. And we apply this Heapify up, uh, like this entire algorithm to the newly inserted node, which is, in our case, it was 11. So we apply this to 11 and we keep on applying it till it reaches the root node. So typically, like since we are only traversing the path, and since this is a complete tree, the height of a complete tree should be proportional to the value of log of number of nodes, and that's going to be true because it is like completely filled. We have discussed like why it should be log n in the previous set of videos, but the total time for execution of insertion, it's going to take like log n comparisons to fix this heap property. So the total time, it's going to be O of 1 plus O of log n, which means it's going to be like log n in our case. In the next video, we are going to discuss like how we delete or extract the minimum element out of this heaps.